let's examine a strategy that we can use to look at a complicated synthetic pathway. And this is retrosynthetic analysis. And it may seem counterintuitive at first, but if we start at the product, then we may have an easier time finding out how to synthesize it. So let's say, for example, and we'll just do an example to talk about how this can work. We would like to make this molecule. And let's also say that while we would like to make this, we're only going to allow ourselves reagents that have 3 or less carbon atoms in them. So we're going to have to break this apart into several pieces in order to make it if we're limiting ourselves that way. Now, the way this works is we start looking for places where we could break this molecule apart, and then think about reactions that we could use to put this molecule together. So one of the options would be looking at where the functional groups are and deciding we could break it at one of the functional groups. So let's try to see what would happen if we break this bond right here. So the way that we start to draw this out, we'll draw this molecule, and then we'll draw a retrosynthetic arrow, which is just an arrow that has a couple lines in it. It's kind of a more open arrow. And the way you would read this is can be made from. So in reality, the reaction is going to go this way, but we're trying to break this apart into more manageable pieces. So let's see what would happen if we break this bond right here. If we did that, we could have a 2 carbon piece here and then a 1, 2, 3, 4 carbon piece there. So we'll still have some breaking apart to do, but we'll be closer to what we need, which is the 3 carbons or less that we've just arbitrarily decided for this exercise. So we need some kind of leaving group over here. So we'll just stick with a bromine here. And then we've got the other molecule that we have here, which is still too many carbons, but this part is only 2 carbons, so we're getting closer. So now that we have that, we'll usually look for another place, another functional group location that we could break this molecule apart at. So here's a good spot right here. And that will get us down to 1, 2, 3 carbons there. This only has 1 carbon. And we have reactions that can make ethers. And so let's just continue drawing in this way. We'll ignore that part right there, but now so we've got a leaving group added onto there, and we're just going to stick with bromines just because it's convenient. And then we need the alkoxide. We're going to do Williamson ether synthesis here. And in this case, we're going to deprotonate this alkyne and then use that to make a carbon nucleophile and attack there, right? So sometimes we don't have to think as much about what reagents we're going to use right away. If we have that in mind, that's great, because we might end up in a dead end location where we just can't go forward, we'll have to try breaking another bond instead of that direction. So once we've conducted the retrosynthetic analysis, then what we'll do is we'll turn around and we'll go in the forward direction and we'll write down all the conditions and we'll really check to make sure that the selectivity is what we need and we are actually going to make the product that we want. So we'll do that now. Starting with the ether synthesis. And the nice thing about ethers is once we add it onto the molecule, generally the functional group is quite tolerant of other transformations, other conditions. So now we've made our intermediate here. At this point, we can form the carbon nucleophile. We can pick sodium hydride or a similarly strong base. And then we'll add our bromoethane. Which will then affect the product that we were looking for in the first place. Now, this is one option for making this molecule, but there is more than one way to usually conduct a synthesis, especially when it gets to be complicated. Now, there's ways that we could use to decide which ones would be better, but let's look at this for now. So let's examine another way to do it. That could be possible. Now, there could be problems with this way. There could be problems with the other way. We'll have to look at that at some point, certainly, hopefully, before we do it in the lab. All right, so this time we broke this bond right here. Instead, what if we broke this one? So we break right there. And then we'll just imagine that we're going to turn this into a nucleophile, carbon nucleophile. So we'll just put a leaving group over on the other molecule. This only has 2 carbons in it, so we're good on that one. This one has 1, 2, 3, 4. So by our own rules, we're going to have to break this part a little bit more. So we could say that could be made from the bromoethane and let's just say acetylene. And so if we wanted to write this in the forward direction, we would do this. Again, we're going to use the sodium hydride. That's an H, not an I. And our bromoethane. We should be able to make this. And then we'll just form our carbon nucleophile again. Same kind of reagents, only now we're going to change to a different substrate. And we could affect our product. Now, I would argue that the first synthesis is a little bit better, simply for selectivity reasons. There's nothing really telling this reaction to stop at only adding on the one side of this triple bond here. And so if we're not careful, and perhaps even if we are, we will get some side reaction where we would make this this reagent or this product, and that's not going to be helpful for us moving forward because we still need this proton available and it's not a symmetrical molecule. So that's one of the things that we may consider. Now, if we had a large excess of acetylene and we really controlled the amount of sodium hydride we had in there, we let this step really come into equilibrium, we could get to where we only deprotonated one of these and acid-base reactions can happen one at a time. Then we add in that second reagent. We'd have to then separate this, and then we could go ahead and add in additional, create that, and create the product. I think that we'd have a little bit easier time with the above reaction, but it's likely that both could be used to make the product. And that's an important point. There are going to be multiple correct ways of doing an organic synthesis, of planning one of these out. And there can be arguments made for why one is better than the other. There could be reasons why you would go with one over another. Chemical availability could be one of those. So there's lots of things to consider, and we'll look at a few of those coming up.